Friends, in lecture 24 in module 2, we will continue with the discussion on unsymmetrical bending. So, for a typical cross section, whose z axis and y axis are shown like this, we picked up a sample area dA. We try to locate the principal axis of inertia u and v with angle alpha. We said that u is z cos alpha plus y sin alpha and v is minus z sin alpha plus y cos alpha. We found I u as simply second moment of area of v square dA, which amounts to I z plus I y by 2 plus I z minus I y by 2 cos 2 alpha minus I y z sin 2 alpha, and I v is integral for the entire area with second moment of area u square dA, which was derived as I z plus I y by 2 minus I z minus I y by 2 cos 2 alpha plus I y z sin 2 alpha. By looking at the above two equations of I u and I v, one can straight away write a simple observation that adding these two I u I v, because the negative cos 2 alpha terms and sin 2 alpha terms will get cancelled, I will get simply I z plus I y, which we said equation 4. We need to also work out I x I z y, or let us say I u v, which is integral for the entire area u v dA, which is now z cos alpha plus y sin alpha into minus z sin alpha plus y cos alpha of dA. Let us do this multiplication for the entire area A. Minus z square sin alpha cos alpha minus y z sin square alpha plus y z cos square alpha plus y square sin alpha cos alpha of dA integral for the entire area A. We know integral z square dA will lead to I y, integral y square dA will lead to I z, integral y z dA will lead to I y z. Using this relationship, for the entire area. we can now write IUV will be minus IY sin alpha cos alpha plus IZ sin alpha cos alpha plus IYZ cos square alpha minus sin square alpha, which can be now said as IZ minus IY by 2 sin 2 alpha, because 2 sin alpha cos alpha is sin 2 alpha and cos square alpha minus sin square alpha is cos 2 alpha. So, plus IYZ cos 2 alpha, that is IUV. For U and V be principal axis of inertia, IUV should be 0, that is IZ minus IY by 2 sin 2 alpha plus IYZ cos 2 alpha should be set to 0. So, by rearranging, you will know that tan 2 alpha is minus 2 IYZ by IZ minus IY. For our clarity, we call this alpha 1. So, alpha 1 is inclination of positive u axis with respect to z axis which is also positive. So, let us go back to this figure and mark alpha. So, alpha is once again explained. If this is my z axis, this is my positive y axis, and I want to mark the u positive. If this is my positive u axis, this becomes my alpha 1. Where alpha 1 is inclination of the positive u axis measured from positive z axis. Having determined the principal axis of moment of inertia, the next step is to determine the bending stresses at any point in the cross section. So, let us say this is my beam which has a cross section of some shape. We have the z axis and the y axis and the x axis marked like this. In this plane, we will also try to mark the u axis. We know this angle now is actually alpha 1. This is my u axis and this becomes my v axis. So, let us pick up this cross section and try to mark only the axis which is y, which is z. Let us also mark the u and v with a point P where I want to find the bending stress. Let us use to mark the moments, sign convention to mark the moments. About an axis. We will use right screw rule. So, let your thumb face the positive direction of axis and try to screw along the axis like driving a screw with the help of a screwdriver. You will notice that this will become my direction of mz, this will become my direction of mv, and this will become direction of mu, and so on. We already have this angle, we call this for our understanding as alpha, because alpha 1 is for our understanding to clarify it is between two positive axes. Actually, the angle between the z and the u axis is alpha. So, from this figure one can write that mu is mz cos alpha and mv, if you try to resolve this moment, about v, you get this as minus mz sin alpha, because this mz when you try to resolve along the v axis comes to be in the negative side. So, equation number let us say 1. So, stress at any point which is described with the coordinates u v. We are not working on x, z, y anymore. We are transforming the problem of unsymmetrical bending to uniplanar bending. So, instead of z y axis we will work out with u v. The advantage is if I am able to locate the principal axis of inertia u v and try to find the stress about this with the coordinates, I can use a conventional flexure formula, which can be mu by iu into v, which will cause compressive stress, and mv by iv into u, which will cause tensile stress. Let us try to understand how do we look this nature of the stresses. So, let us look at mu, which will create a bending of this nature. So, this will create bending of this nature, which creates compression at the point in the positive coordinates. If you look at mv is applying moment of this order, which will create tension here for MV. So, MU will result in compression and MV will result in tension. Now, let us consider tensile stresses as positive. So, stress at point P is actually minus MU by IU into V plus MV by IV into U. Instead, I can even say MU by IU into V minus MV by IV into U. Equation number 2. Negation indicates compressive stress. Let us summarize and then do a problem. What are the steps to compute stress at any point under unsymmetric bending? When the cross section is subject to unsymmetric bending, one can follow the following steps to estimate the stresses. Find Ix, Iy and Ixy of the cross section, which are from the standard equations for a given cross section. 2. Locate the principal axis of inertia u and v. So, compute Iu, Iv, and we know Iuv is 0 and alpha. To be very clear, alpha 1. Please understand, alpha is measured positive with positive V values. Okay. Then once you locate the principal axis of inertia, use the standard equation of flexure to estimate the bending stress. So, friends, let us take an example problem to understand how to locate this principal axis of inertia, so that by locating these axis of inertia and marking neutral axis with respect to this, I can use the conventional equation of flexure to obtain bending stress at any point in the cross section. So, we will take an example. The example is to locate the principal axis of inertia and to determine Iu, Iv for a given section. We will take this as an example. We will take a Z section The dimension section are given like this. This is 80 millimeter, all dimensions are in millimeters. The thickness is 10 millimeter. The overall depth of the web is 150. The section has uniform thickness through and through of 10 millimeter, and the top flange is also of 80 millimeter. So, this section has two axes of symmetry. Let us locate them. Let us say this is my z axis, and this is my y axis, and this becomes my C g. Both these are axes of symmetry, but they are not principal axes of inertia. We need to locate them for this given problem. Let us first try to find the moment of inertia of the section about these two axes I z. We can do this by using the conventional principal axis theorem. So, I call this as piece 1, this as piece 2, and the web as piece 3. Each one of them have the local C g, which we need to estimate the coordinates to find the moment of inertia about the z and y axis. So, I z for member 1 80 10 cube by 12 plus area into k square. So, this distance is what we are interested in, which will be 75 minus 5, which is 70 square. This is for member 1 or the top flange, plus let us do it for the bottom flange as multiplying this by 2, plus let us do it for the web, which is member 3, which is 10 130 cube by 12. So, I substitute this and get this value as 9.684 10 power 6. Similarly, I can find I y for member 1 10 80 cube by 12 plus 80 into 10. Now, I would like to find this distance, which will be 40 minus 5, which is 35 square. This is for member 1 and 2. So, multiply this by 2 plus for the web it is 130 10 cube by 12, which now gives me 2.824 10 power 6 mm4. Now, the tricky part, we would like to get the product moment of inertia I z y. I z y by definition is z y dA integrating for the entire area. So, we have divided the section into 3 components. We would like to find the z and y coordinates of all the 3 components and sum them up to get I z y. Please note, I z y can be negative as well, but I z and I y will be always positive. Now, let us try to find I z y. So, I z y now going to be the top flange 80 into 10, the z and y coordinates of this flange, the z coordinate will be positive for this case. So, it is plus 35, y coordinate is also positive 70, this for member 1. and for the bottom flange area will be again same, but the z coordinate will be, the dimension is same, but it is minus 35 because it is in the opposite direction of z, and similarly this distance is opposite of y. So, minus 70, this is for the member 2, and for the web the zy coordinates will match, and therefore, it is 0 for member 3. Summing up, we get Izy as positive 3.92 10 power 6 mm4. Now, we need to locate the principal axis of inertia, that is u and v axis. So, using the same equation what we derived, we know that tan 2 alpha 1 is minus 2 y z by z minus y. Substituting, we get 2 of 3.92 10 power 6 by 9.684 minus 2.824 of 10 power 6, which gives me minus 1.143, which now tells me 2 alpha 1 is 125.28 degrees, or alpha 1 is 62.64 degrees. So, let us go back to this figure and locate the principal axis. So, this is my 62 degrees, and this is my u, and this becomes my v, and this angle becomes my 62.64 degrees. So, it is expected that since u and v are principal axis, I u v will be 0. Let us try to find I u from the equation I y I z by 2 plus z minus y by 2 cos 2 alpha minus I y z sin 2 alpha. Substituting 2.824 plus 9.684 10 power 6 by 2 plus 9.684 minus 2.824 10 power 6 by 2 cos 125.28 degrees minus 3.92 10 power 6 sin 125.28 degrees, which gives me the net value as 1.054 10 power 6 mm4. Similarly, I v, this can be easily solved by simply saying I z plus I y minus I u. So, which we say 9.684 plus 2.824 minus 1.054 of 10 power 6, which gives me 11.454 10 power 6 mm4. So, for a given section which has axis of symmetry, we can easily locate the principal axis and find the moment of inertia about this principal axis. That is example 1 as described. So, let us talk about example 2. To find the stresses due to applied moment. Let us take an example of a cantilever section whose cross section is an angle which is fixed. It has got two axes. Let us mark them as z and y. We will also apply a force which is P equal to 2 kilonewton, which is over a span of 2 meters. Let us draw this cross section separately. And write down the geometric properties. Let us say this dimension is 50, all in millimeters. This dimension is 30 and the thickness through and through is 5 millimeter. Let us mark these axes as z and y, and this is my CG. So, from the first principles one can easily calculate the value of y bar and z bar. So, let us do that quickly to understand. So, y bar is simply sigma a y bar by sigma a, and z bar is simply sigma a z bar by sigma a. Applying these equations, let us try to find y bar. So, let us talk about the top flange. So, let us say the top flange is taken like this. So, 30 into 5, that is the area. We are measuring it from the extreme end, therefore, the distance is 2.5 millimeter plus. Let us talk about this flange. Let us say this is piece number 1 and this is piece number 2. This is for the first piece. The second piece, let us say 45 into 5 is the area, and the distance of this from here. Okay. So, 45 is 22.5 plus 2.5. Okay. So, I should say 22.5 plus 5 divided by area 30 into 5 plus 45 into 5, which gives me y bar as 17.5 millimeters. Now, to locate z bar, we do the same thing. Let us measure z bar from the extreme right, that is my origin, okay, that is my origin, extreme right. I am measuring z bar from here, okay, from here. So, the top flange 30 into 5 is the area and the distance will be 15, and the vertical flange, that is piece number 2, 45 into 5 is the area and the distance is 2.5. The total area 30 into 5 plus 45 into 5, which can be 7.5. So, y bar is 17.5 and z bar is 7.5. So, with this data, let us compute I z and I y. Let us draw the cross section again. Let us locate the centroidal axis. Z and y. This is 17.5 and this value is 7.5, and the dimensions, this is 50, this is 10 and this is 30. So, from first principles I can find I z, that is 30 into 5 cube by 12 plus parallel axis theorem, which will be 17.5 minus 2.5 whole square plus 5, oh this is 5 mm thick, 5 into 45 cube by 12 plus again parallel axis theorem 45 into 5 into 27.5 minus 17.5 the whole square, which gives me 9.453 into 10 power 4 mm4. I y phi 30 cube by 12, the piece is divided like this, plus 30 into 5 into 15 minus 7.5 the whole square plus 45 into 5 cube by 12 plus 45 into 5 into 7.5 minus 2.5 the whole square, which gives me 2.579 into 10 power 4 mm4. Let us find out I y z. Which will be, let us say for the top flange piece number 1, 30 into 5, the positive z coordinate which is 15 minus 7.5, which is positive, because the CG of this lies here, which is positive, into 17.5 minus 2.5, that is this distance, which is also positive in y. That is for the top one, piece number 1, plus for piece number 2, 45 into 5 is the area, CG is somewhere here. I am looking for this distance, which is negative in z axis. So, I should say 7.5 minus 2.5, but negative. Similarly, I am looking for this distance, which is again negative on y, which is minus of 27.5 minus 17.5. Okay. So, that is for the piece number 1, and this is for the piece number 2, this is piece number 2. So, piece number 2 has got z value negative and y value negative. So, this is 7.5, this distance 7.5 and this distance is 2.5, okay, that is what we have done here, and this distance is 45 by 2 and from here it is 27.5 and this 17.5. So, this distance minus this is what we have here. So, I y z after calculation comes to 2.813 10 power 4 mm4. So, now I can quickly locate tan 2 alpha 1, which is minus of 2 y z, but z minus y, which is minus of 2 of 2.813 10 power 4 by 9.453 minus 2.579 10 power 4, which is actually minus 0.818 degrees, which amounts to alpha 1 as 70.36 degrees. The u and v and this angle is 70.36 degrees. Now, one can find I u as I y, I z, I z, I y cos 2 alpha, I z sin 2 alpha. One can substitute for the values cos 2 alpha. So, 140.71 degrees minus I y z, that is 2.813 sin 140.71, which gives I u as 1.575 10 power 4 and I v is I z plus I y minus I u. So, it is 9.453 plus 2.579 minus 1.575 of 10 power 4, which gives me 10.457 10 power 4 mm. So, now I want to find the stresses. So, we have mz, which is creating moment. We have u and v axis, okay, which is alpha 1. So, which will have mu and mv. So, now I can write mu will be mz cos alpha 1 and mv will be minus mz sin alpha 1. So, let us say mu is going to be mz. Let us say what is mz, go back to this equation, the original problem. It is a cantilever with 2 kilonewton for a span of 2 meters. It will make the beam to bend this way. Okay. So, tension at the bottom and compression at the top. The moment is going to be actually 2 into 2, which is 4 kilonewton meter. So, now mu is actually 4 of cos 70.36, which comes to plus 1.344 kilonewton meter, and mv is minus 4 sin 70.36, which is minus 3.767 kilonewton meter. Now, you have transformed the entire problem from the zy plane to uv plane. Okay. So, the stress at any point x should be generally given by mu by Iu into v minus mv by Iv into u. Let us try to extend this discussion for the next lecture and estimate the stresses with this example and one more example which will continue. Thank you very much.